Welcome back to Lesson 1-5 Part 2. We're looking at graphing linear functions and inequalities, and we're going to jump right into this lesson here today. So what we're going to be talking about is shading graphs of linear inequalities. So we looked at equations in our previous lesson, and now we're going to look at inequalities, and that's why there is the shading. There has to be shading in order to prove that it's an inequality. Now think about if I said I wanted x to equal 1, or if I wanted values of x less than 1. Which one has more answers? Of course, if I say x equals 1, it can only be that one value. But if I say x is less than 1, it's everything smaller than 1. It's infinitely many numbers because it's anything that is smaller than 1. So when I'm looking at the graph of inequality and it says y is less than 2x plus 3, well, what we do is we graph that 2x plus 3 as if it says y equals 2x plus 3. We plot our points the same way that we would any other day. But then what we have to take into account is we're looking for the y values less than that. So what we're going to be doing, we're looking for y's less than 2x plus 3. We have to shade, and we have to decide, do we want to include the points on the line? Or do we want to just start at the line and go below? Like with an inequality, if I say x is less than 2, it was everything below 2. But if I say it's less than or equal to 2, we know that that includes 2 and everything less than 2. So with the line, we're looking at, do we include that line? If we do, if it's equal to that line, then we put a solid line. Or if we just say, and then we have to do the shading because it's everything less than or equal to that line. So we have to show all of those other little points are possible solutions. Or we can say if it's just less than, we'll use a dashed line to show that we're starting at this line, but we don't include this line. We start here and it's everything below that line. Or if it's greater than, it's everything above that line, depending on how the case falls. Actually graphing it, we're just kind of exploring some things here. And what it wants me to show you looking at this is it's still saying less than, but so this point right here, -4, -1, if I was to plug it in, -4 in place of x and -1 in place of y, that should be less than 8. But look what happens when I come over here. My sign switched to greater than. Now it is greater than. So the point of this exercise here is to show you that not every point on the graph is going to make the inequality true. If I get down here, I have to change the direction of the inequality symbol because if I kept it less than, it would no longer be a true statement. Let's look at the numbers, plugging it in. 3 times 3 is 9. 9 take away 8 is 1. What am I looking at? Oh, 9 plus 8 because it's a negative times a negative. So 9 plus 8 is 17. And of course, 17 is greater than 8. So that symbol had to change. We couldn't keep it the same or it would no longer be a true statement. So that's what happens when we graph. We have to decide which side of the lines are the points on that make it a true statement. And whichever side they're on, then that's the side that we shade. So that was the purpose of this activity. So what we're going to do now is we're going to look at some vocabulary. The graph of a linear inequality is a half plane with a boundary that is a straight line. So this is my straight line here that's bounding this half plane that's been shaded. The half plane is shaded to indicate that all the points in this yellow region are solutions to the inequality. A boundary is a line or curve that separates the coordinate plane into two half planes. The boundary is solid. The boundary line here is a solid line when all of those points on the boundary line are included, when they're possible solutions. Okay, and if it is a dashed line, then that means that the points on the line are not included in the answers. So then this results in an open half plane. So if it's a solid line and we're including the solutions on the line, then it's called a closed half plane. But if it's a dashed line and we don't want to include the points on the line, then we call it an open half plane. So let's watch this little video here. I like their videos. I think they're really, really good explanations. So in your video, you're going to watch a video.
To graph a linear inequality in two variables, begin by graphing the boundary.
So we went up 1 over 2 using the slope.
Use a solid line for an inequality that includes a less than or equal to, or a greater than or equal to symbol. Use a dashed line for an inequality that includes a less than or a greater than symbol. Next, use a test point to determine which half plane should be shaded. Selecting 0, 0 as a test point often makes calculations easier. Then, shade the half plane that contains the solution set. If the test point makes the inequality true, shade the half plane that contains the test point. If the test point makes the inequality false, shade the other half plane. To check your solution, identify a point in the solution region. Substitute its coordinates into the inequality to check that it makes the inequality true.
All right, so that's just a really quick visual of what I just previously stated, but they started by graphing the y-intercept, used the slope then to rise 1, run 2 to find our next point, and they used a dashed line to show that we're not including these solution sets. Look at the point 0, 1. If I was to plug that in, 0 for x, I have 1/2 times 0 plus 1 is less than, and then my answer is 1. Well, of course, 1/2 times 0 is just 0. Is 1 less than 1? No, 1 is equal to 1. It's not less than 1. So that point is not true. That's why we don't want to include that point on our line, or why we don't want to make it a solid line, because none of these points on that line are true. If it said less than or equal to, then we would make a solid line, and that would be true. 1 is less than or equal to 1. It's equal to it. So that's the difference in why we would use the solid and the dashed line. So looking at example 4 in your workbooks on page 41, we're going to graph an inequality with an open half plane. So step 1, we've got to graph the boundary. So I would begin by converting this into slope-intercept form. So we're going to move the 12 over to the other side. It becomes a negative. Then I divide everything by -4. So now my slope is -1/4. And my -12 divided by -4 is a +3, making my y-intercept a +3. So now we can graph this line. Starting at a +3 on the y-axis, then my slope tells me go down 1 to the right 4. That gives me a downward motion, so my slope's going to be negative. Okay, now, why use a dashed line? Hopefully you're getting this here. It's less than. It's not the points on the line. It's everything less than the points on the line. So we can pick out our test point, 0, 0, plug it in and see if it's true. Is 0 less than 3? Yes, it's true. So we want to shade all the points below the line. If I had tested that out and it was false, then I would know we don't want to shade the side that includes that. We must shade the opposite side. And then we could pick another test point and just check to see if it worked. All right, and example 5. Graph an inequality with a closed half plane. That previous example was open because it was a dashed line. So now we're going to look at one that's going to be a closed half plane. And so therefore I know when I see the word closed half plane, it must have an equal to in the problem. We look at this inequality and there is a less than or equal to. So we're going to begin by moving the 9 over to the other side. Something I forgot to mention, point out to you, it just occurred to me in that previous example, was that when they divided both sides by this -4, this is something you learned in Algebra 1, but if you divide both sides of the inequality by a negative, do not forget to reverse that inequality symbol. It says it on here, but I didn't point it out, so I wanted to make sure to come back and do that real quick. Okay, so looking back at this problem, we're moving that 9 over. It's going to be a negative. Then I divide everything by 3. So I get 8/3 x minus 3. Now we can start to graph. Plot that y-intercept down here at -3. We rise 8. 1, 2, 3, 4, 5, 6, 7, 8. Run 3. 1, 2, 3. Connect those points with a line, and we use a closed half plane, a solid line, because it's equal to. If I pick this point 0, -3 and plug it in, I get -3 is less than or equal to -3. That is correct. It's equal to -3. So we want to include that point. Pick our test point, 0, 0, plug it in. I believe it shows that here. Using the test point 0, 0, they plugged it back into the original equation, which is a good idea just in case you made a mistake mathematically somewhere along the way. This might help you catch that mistake. So they plugged in 0, 0. It was a false statement, so they don't want to include the side that, or they don't want to shade the side that includes that point. They want to shade the opposite side. Since 0, 0 created a false statement, 9 is not less than or equal to 0. We don't want to shade the side that includes that. We want to shade the opposite side that does not include that point. You could pick another test point just to check it. They picked 3, 1. Go over 1, 2, 3, up 1. That's in our shaded region. Let's check and see if it's true. It is true. 12 is less than or equal to 24, so we know we shaded correctly. And our last example for the day says grades. Malik's algebra teacher determines semester grades by finding the sum of 70% of a student's test grade average and 30% of a student's homework grade average. If Malik, I don't know if I'm saying that right, you can say whatever you want. If he wants a semester grade of 90% or better, write and graph the inequality that represents the constraints for Malik's test grade X and homework grade Y. So what are constraints? Constraints are the part of the problem or condition, it's like a condition in the problem that the solution must satisfy. So let's look at this. Finding the sum of 70% of a student's test grade average and 30% of a student's homework grade average. He wants a 90% or better. So let's think about the task here. Describe the task in your own words. Then list any questions that you may have. How can you find the answers to your questions? Let's think about this for a second. Go ahead and pause the video. So our task here is to figure out what it's really asking us. We've got to use this description to write that inequality, and then once we have that inequality, we can graph it, and we can look at the constraints. We can look at the boundary lines, use a test point, and figure out what should be shaded. So that's our task, to write an inequality, then to find points and figure out where that boundary is and create the graph. All right, so how are we going to approach the task? What have you learned that you can use to help you complete the task? Well, once you have that inequality, we've learned how to graph it. We've learned how to choose a test point and how to determine which side to shade. And so what is your solution? Once you solve it, what inequality is going to represent the constraints for Malik's, test and homework grades? So let's think about this. What did the problem say? It said that the sum of 70% of a student's test grade average and 30% of the homework average, he wants a semester grade of 90% or better. So we know that he has to have 70%. How do we represent 70%? 0.7, right? That's 70%. It's going to make me click here again. So 0.7, try this again, 0.7% of his test grades, we'll let that be X. And we're going to add that because it said the sum, didn't it say the sum? The sum of 70% of his test grades and the average, and 30% of his homework average. So how do I show 30% of his homework average? 0.3 times the homework average. And for him to get the grade he wants his to be, what did it say? Greater than or 90% or better. If he wants it to be better than 90%, then we know he's wanting it to be greater than or equal to, because he says 90% or better. So greater than or equal to 90%. All right, so now we've got our inequality. We can graph it. Let's see if this is correct. Uh-oh, it says it's not right. I have a feeling that it's saying that it's not right because I did not put this 0 in here. Bad algebra teacher. Now let's check it. Yay! Very tricky. It's very picky, isn't it? So which of these are viable solutions? Viable just means possible. Like which of these are possible solutions for his test and homework grades? Well, let's plug it in. 88%. So if I plug in 88 here and 100 here, is it going to be true? You can do the math. Yes, that works. If I plug in 90 and 90, does it work? Yes, it does. You can plug it in and do the math. If I plug in 90 and 80, no, that's not going to give me a score greater than 90. Do the math, complete it. If I plug in 95 and 70, nope, doesn't work. How about 95 and 80? Plug it in. Yes, that works. How about 170? Yes, that works. We can complete the math and check it, and that gives us the correct answers. So how can you show that your solution is reasonable? Well, what we could do is we could graph this on the graph and then show that these are points in the shaded region, that when x is 0.88 and y is it'd be 1, not 0.1, that'd be 10%, but 1, then that is an area in the shaded region. That is an area in my shaded region on my graph once I graph it and plot it. I hope that made sense. I went through that kind of quickly. If you need to go back and rewatch sections, don't think just because you're done, you're done. You can go back and watch. You can fast forward. I know you guys are high school students and you already know this, but my son is an elementary student and he had already watched a video and there was a part that he really that he was really unsure about. And I said, well, go back to the video and watch it a second time. And he said, no, I don't want to watch it. It's like 20 minutes long. And I'm like, well, don't watch the whole video again. Like fast forward to that part. And he said, no, my teacher will think that I didn't watch the video, that I just watched that little section. I have to watch the whole thing. I thought that was really cute that he thought he couldn't fast forward. Obviously, you guys know that you can do that. And you probably fast forward. You're fast forwarding through what I'm saying right now because you don't really care about it, most likely. But go back and watch the parts that didn't make sense. If you're trying a problem in your homework, go back into the section. Like usually the homework tells you like this mimics example 4. So go back if you're having trouble to example 4 and follow along, watch it again, and it might refresh your memory or something might make a little bit more sense the second time. So that is all I have for today. I hope you guys have a great day.